In this lesson, we're going to discuss analysis of variance, or ANOVA. So the objectives are to provide a brief review of ANOVA, the basic concepts of what ANOVA does, understand how the F statistic is calculated, because the F statistic is the statistic underlying ANOVA results that allows us to generate p-values. We'll understand how to use proc ANOVA and interpret the results in SAS. And I'll also show a few examples of how you can correct for multiple comparisons in an ANOVA setting. And then finally, we'll talk briefly about how to use proc box plot so that you can visualize your data according to the exposure variables or the groups of interest that you may be modeling within ANOVA. And I'll say up front that, again, if you have extensive experience and expertise in statistics and epidemiology, you may want to skip through the initial portion of this conceptual overview to ANOVA, because that will be quite familiar to you, and jump midway through to the applied piece. Analysis of variance is a method that's used to compare multiple means. So for example, you may think about asking the question of whether or not age varies by region. Age is a continuous outcome variable or dependent variable, and region has 4 categorical levels. Or alternatively, you could think about, as we have been in the examples oftentimes in this course, whether or not mean blood pressure varies according to BMI categories. So in those examples, we often think about systolic blood pressure as a continuous variable, and we look at how the means vary according to BMI categories. In the 2-sample t-test scenario, we performed some t-tests to see whether or not mean systolic blood pressure was different according to two-level BMI category, people who were, for example, normal weight or overweight and obese. But the t-test does not handle situations where your explanatory variable has more than 2 levels, and ANOVA can help us with this. So you can see how this example extends to many different settings in epidemiology. So the core notion here is that your explanatory variable is some sort of, usually some sort of well-defined categorical variable, and the outcome variable is a continuous variable. As I said, this is really an extension of the 2-sample t-statistic to consider groups with more than 2 levels. And the core null hypothesis, or H0, is that the many different population means are equal, or in other words, systolic blood pressures are equal across all levels of BMI. So a very important concept, as you would imagine, in ANOVA is the comparison of between versus within group variation. ANOVA is about the analysis of variance, and in that context you're thinking about the variability of the data that's explained by the group relative to the variability of the data within a group. So if you have a situation where a variable is a very powerful explanation of your outcome, then you would see that group variation will be large, particularly relative to the amount of variability you would see between individual within group. And based on that information, you can calculate an F statistic for hypothesis testing, and the F statistic simply represents a ratio between group variation and within group variation. So in this context, we're trying to think about what actually causes, or at least predicts or is associated with variation in some dependent variable. So in this particular lesson, let's talk about an example where we think of smoking status predicting systolic blood pressure. And the basic modeling assumption within ANOVA is that the observed value I can be predicted by some grand mean, so mean systolic blood pressure, and then adding on some deviation from the grand mean that is related to group membership, and then finally a residual. And based on that notion, let's talk a little bit about how the model works and how we actually get to the F statistic. So first, again, we consider our sources of variation in an ANOVA model. And the basic setup is that you have some variation in the data that's explained by your model, however the model is set up, plus some residual error. Or in other words, in ANOVA phrasing, there's a sum of squared variation total for the overall data, and that can be broken down into variation explained by the model and by the error. And within SAS, you'll see the word model quite frequently. Some textbooks would, instead of using the word model, would use the word groups, for example. But SAS will provide output that uses the word model and error. How do we get or actually calculate this variation for the overall variation and then the components based on the model and the error? The calculations are pretty straightforward. The sum of squares total in your model is simply going to be equal to the sum of the squared differences between each observed value and the grand mean. So in the example we're using, we would be thinking about the difference between each observed value of systolic blood pressure and its difference from the overall mean blood pressure in the data set, and then you square that for each individual, and you sum those up across all individuals in the data set. The sum of squared groups is defined by looking at the difference between the group mean and the grand mean for every individual in the data set and squaring that and summing up across all observations. And the sum of squared error is derived by looking at the difference between each individual within group and subtracting off the actual group mean. And again, squaring those for each individual in your data set and summing them up. Now, since there are different ends essentially contributing to this variation, we want to standardize the variation according to the number of factors that are explaining it. And to do so in ANOVA, you simply divide each of the sources of variation by corresponding degrees of freedom. For the sum of squared group, the degrees of freedom is defined by I minus 1, where I represents the number of groups. In our example, we'll have 3 groups, never, former, and current smokers. So the sum of squares group would be 3 minus 1, or 2. And sum of squared errors is defined by n minus I, which is simply the total sample size minus the number of groups. And then you calculate a mean square. So the mean square, as I alluded to previously, is simply the sum of squares group. The mean square group is simply the sum of squares group divided by its degrees of freedom, and the mean square error is the sum of squares error divided by its degrees of freedom. And then you can take a ratio of the mean square group to the mean square error, which will generate an F statistic. And then finally, we can use that F statistic in combination with degrees of freedom to find some probability for observing the data that we have. So as you can see, the F statistic fundamentally, again, is really just some ratio of a measure of variability based on group membership relative to variability that the model doesn't explain. This is a quick reminder of what an F distribution looks like. So I'm showing 2 different examples here, one with degrees of freedom 4 and 12. So in this example, you would need an F statistic of 3.26 or greater to reject the null hypothesis with an alpha of 0.05 or 5% type 1 error. And in the second example, this is an F distribution with degrees of freedom 10 and 100. And in that scenario, you'd need an F statistic of 1.93 or greater to reject the null hypothesis. Again, the null hypothesis is simply that all group means are equal. Well, let's consider just a quick theoretical example for teaching purposes. Imagine we have a data set with 15 observations. So these are just the ID numbers for each of the 15 participants. The second column has systolic blood pressures for each of them. And the third column represents smoking status. They can have a smoking status of 1, 2, or 3. And in this example, 1 corresponds to a current smoker, 2 corresponds to a former smoker, and 3 is a never smoker. So if we just change the data structure a little bit to look at this in a slightly different tabular format, you can see it a little bit more obviously and intuitively how group means vary and how individual values vary within group. So if you consider current smokers in this extreme teaching example, everybody has exactly the same systolic blood pressure, so there's no variability within group. And the same is true for the former and the never smokers. The group here seems to be explaining all variation in the data, and there is variation because the group means do change, and you can see that intuitively by all the individual systolic blood pressure values because they're not all identical for every individual. So taking that example, let's jump into SAS here in a moment and actually run an ANOVA on a data set with those actual values and see what our results are. So to do that, let's create a format using proc format. Define your new format rules and label the formats as current, former, and never, such that 1 is set equal to current, 2 is set equal to former, and 3 is set equal to never. And then try running the code below using the editor file provided for this lesson. So before you run this code, you'll have to run a short data step to generate the smoke data set, and again, that's provided in the editor file. Go ahead and pause now and run that, and then come on back in and we'll go into SAS and take a look. Okay. So first I'm just going to create a new SAS data set. I'm going to read in some raw data from the data lines because it's a very small data set put together for teaching purposes. And if you wanted, you could copy and paste this data step and actually manipulate the different values for systolic and diastolic blood pressure to some degree if you wanted to run ANOVAs based on a different data structure. We'll run that and a quick proc print just to look at the actual data set. So again, we have smoking status represented by the smoke variable, and then systolic and diastolic blood pressures represented by SBP and DBP. There are 15 observations in our data set. Here's the proc format we talked about using to set up a new SAS format that could be applied to the smoking variable. I named the format SMKF. You may have chosen a different name. It's perfectly fine. And the rules of the format are that values of 1 are equal to the word current, values of 2 receive the word former, and values of 3 receive the word never in the output window. So I'll run that proc format. And in the log file it says the format SMKF has been output. I also have a note that it's already on the library. That's actually because I ran it prior to starting this lesson. So it just redefined and wrote over the previous format that I had created earlier. So in proc ANOVA, we're running an ANOVA. It's a procedure. So again, we start with proc, specify the name of the procedure, and the data set on which you want to run that procedure. We're using the temporary SAS data set named smoke that we created just above. Then I'm adding a format statement so that I can apply this format created above to the smoke variable, which is the explanatory variable of interest. And I'm doing that simply to make the output more readable so I remember who the current and the never smokers are. Then within proc ANOVA you would use a class statement, and the class statement is where your explanatory variable or variables are put. If you wanted to use more than one explanatory variable, you could add it next to smoke in the class statement. And then we have a model statement. So the model statement and the class statement are the two most important aspects of Proc ANOVA, because it's really telling ANOVA how to set up the actual model and run the analysis. In the model statement, you're simply specifying the word model, which is the keyword, and then you want to provide the variable name for your dependent variable and set it equal to the independent variable or variables that you want to include in your ANOVA. So here we want systolic blood pressure to be predicted by the smoke variable. And then I'm also adding a means statement, and what that will do is it will, in addition to giving us the ANOVA table and F statistic, it will print out the mean systolic blood pressure according to categories of the smoke variable. We can highlight that and submit it. Scroll to the beginning of the output. We have some basic information about the ANOVA, the number of observations included, and here's the ANOVA table. And you can see in this extreme example that the model has a sum of squares equal to 250 and a mean square equal to 125, so that's simply 250 divided by 2. And the variation related to error, or sum of squared error, is 0, of course, because as we saw, this was set up as in an arbitrary sense to show an extreme example where all of the variability is between group and there's no variability within group. In other words, our model perfectly explains the data. And if you look at the ratio of the MSG to the MSE, of course you get a value of infinity, which of course then translates into an extraordinarily low p-value, where you can reject the null hypothesis and conclude that the mean systolic blood pressure differs according to levels of the smoke variable. The ANOVA by default gives you some other information as you see below. Some of it is redundant, but you get an R-square coefficient of variation, the root mean squared error, and you get the mean value of the dependent variable. So these are explained a bit more in the slides for this lesson. I'll just briefly note that the R-square is simply telling us what proportion of the total variation is explained by the groups, and that's calculated by taking the model sum of square divided by the total sum of square. So in this example, 100% of the variability in the outcome is explained by our smoking variable. Let's create an alternate data set that's maybe a little bit closer to reality, where there's variability both between and within group. Run that. If you wanted, you could run some proc means and look at the data within proc means. I'm just going to skip down and run the ANOVA that I've set up. So again, we have a class statement where the explanatory variable goes. The explanatory variable is smoke in this example. And then a model statement that specifies systolic blood pressure, the SBP response variable, set equal to smoke, our explanatory variable. And then I've added the mean statement so that we can see mean systolic blood pressure according to smoking category. The beginning of the output. Now in this example, we see the ANOVA table. There's more variability in this data set overall. 512 is the value that we have. The model sum of squares is 443. The sum of squared error is 69. And then the corresponding MSG and MSE are 221 and 5, which results in an F value of 38. So this is a very high F value, and it corresponds here to a p-value of less than 0.0001. So we would reject the null hypothesis again for these data and say that the mean systolic blood pressure values are not equal across smoking categories. the R square is 86, or in other words, 443 divided by 512 equals 86%, and that tells us the model is explaining 86% of the variability in systolic blood pressure. And then if you scroll to the next page, this is what the mean statement provides. So it's simply showing us the actual mean values of systolic blood pressure across level of smoking, as well as the standard deviation. And this is nice information to have because it helps us characterize the data patterns a bit better. And it seems that there's really no variability between the current and the former smokers, but the never smokers seem to have substantially lower systolic blood pressures on average. I've provided the output in the slides as well, so you have it there. This is just output that we saw in SAS. These are some additional descriptions of various pieces of the default output in ANOVA. Now let's talk a little bit about moving beyond the general ANOVA null hypothesis. So again, H0 in an ANOVA setting is that all population means are equal, and in some situations you may want to test specific hypotheses, or in other words, even though you run an overall ANOVA to see if group means, if there's any evidence that the means vary at all across level of your explanatory variable, maybe you want to compare mean levels between various groups within that framework. For example, we may want to compare and see whether or not the systolic blood pressure is actually different between the former and current smokers, or if there's no evidence to reject that null. And in a similar fashion, we could compare the current smokers to the never smokers and the former smokers to the never smokers as well. There are different approaches to accomplishing that in SAS. One approach would be to simply create a format that would group the smokers as maybe ever smokers or never smokers, and then assign the format using a format statement in your procedure. Another option would be to just simply run another data step or include in your original data step the appropriate code to create an alternate smoking variable that would define smokers as ever versus never, if that's the comparison we were interested in. It's actually a reasonable comparison here because it looks like most of the variability is explained by being an ever smoker versus a never smoker in this made-up data set. And there are also several options available within the mean statement that will allow you to do various pairwise comparisons. And we'll talk about that in a moment. So first, let's go back into SAS and test this null hypothesis that ever smoker systolic blood pressure is equal to the mean systolic blood pressure in the never smokers. Here I've created a format, and this format again is simply grouping the ever smokers together, so I'm naming the new format smoke2f, values of 1 or 2 for the variable I apply this format to would be defined as ever, and values of 3 would be defined as never. Submit that. Then I'm going to run my ANOVA. So here I have the format statement where I'm assigning the smoke2f format from above to the smoking variable. Then I specify my explanatory variable smoke in a class statement. I tell SAS what model I want to consider using a model statement, and I want the variable SBP to be set equal to smoke. In other words, how does smoke predict variation in systolic blood pressure? And again, I'll use a mean statement here so that we can look at mean systolic blood pressure according to levels of the smoke variable. Here are the ANOVA results. The total sum of squares is about 513. The model here explains the model sum of squares is equal to 440, and the sum of squared errors is equal to 72. And this generates an F value if we look at the ratio of the MSG to the MSE of 79, and again, a highly statistically significant finding. The R square is very similar to what we saw in the previous ANOVAs. About 86% of the variation in systolic blood pressure is explained by our model. And now in the mean statement, we can see the mean systolic blood pressure among the ever smokers and the never smokers. Again, these are grouped as ever and never smokers in this fashion because we applied a format statement that grouped individuals in this way. If you didn't want to do that, you could simply go back and remove the format statement from that procedure and rerun it, and we'd be back to the situation where we have three unique groups, former, current, and never smokers. As I mentioned, there are also some approaches and options that can be used within the mean statement that will allow you to get multiple pairwise comparisons within the groups of your explanatory variable. And you can also adjust for multiple comparisons within that context using a number of different options. I'm really going to demonstrate and talk about two key different options. And if you're interested in other approaches, particularly those of you who have advanced statistical backgrounds and you prefer another adjustment for multiple comparisons, you can go to the SAS help, read up on Proc ANOVA, specifically the mean statement, and in that context, they'll provide a number of different options that can be used for multiple comparison adjustment. So here we'll talk about the least squared difference and how to obtain that. And what this will do is perform pairwise tests. And note that, again, this is different than a paired t-test. By pairwise test, I simply mean comparing the differences between various combinations of groups, two-way combinations of groups in the data. So in our example, we have three different groups of smokers. So we compare the never smokers to the former, the never smokers to the current, and the current to the former. We can see what the differences are and get an estimate of statistical significance. Note that with the LSD option, there's no control for type 1 error, so the experiment-wise error will be high. You can also use a Bonferroni option by specifying the BON option. So this is a very conservative adjustment for multiple comparisons that most of you are probably familiar with, but you essentially divide your desired alpha, typically 0.05, by the number of comparisons being made. And in our example, we'll have three comparisons. So with an alpha of 0.05 and three comparisons, it's going to only reject the null hypothesis when the p-value is less than 0.017. And the Bonferroni will control the experiment-wise error rate, but type 2 error is increased. In other words, you're much more likely to not reject null hypothesis that should be rejected. And the lines option can also be helpful within the mean statement when group sample sizes are not equal. So I recommend that you give that a try on your own, try and read up in SAS about what the lines option would do, and apply that. In the meantime, we can run a Proc ANOVA and add these LSD and BON options to the mean statement and take a look at the results. So as we've seen before, options quite frequently come at the end of a statement after a forward slash. In this context, any options you might want to add to the mean statement would be added as such. So I've added the LSD and BON options. So here's the Proc ANOVA. Again, the only real change from previous ANOVAs we've run is that I have the LSD and BON options in the means statement. So here's the beginning of the output. These results are similar to what we've seen before. And here's the output for the LSD option. So it's simply telling you what your alpha is, degrees of freedom, and some other useful information, particularly the least squared difference, which is simply telling us that given these data, you would need to see a difference of at least 3.3 millimeters of mercury between two groups in order to reject the null hypothesis using an alpha of 0.05. And here you see the actual means presented, and you have a little description here that says means with the same letter are not significantly different. That simply means if you compare the current smokers with the mean blood pressure of 131.6, there's an A next to the current smokers' mean value, and you can compare that to the former smokers with the mean systolic blood pressure of 130.6, and there's also an A next to that mean value. So those two means are not significantly different at an alpha of 0.05. Alternatively, former smokers with a mean value of 119.6 have a B indicated or listed next to the mean value, which says that it is different than the former or the current smokers because the letters are different. And you can scroll down one more page in the output, and this provides the results for Bonferroni multiple comparison adjustments. So of note, you can notice here that the smallest significant difference, or the smallest difference between mean systolic blood pressures, has now gotten larger because we're being more conservative, and that value is now 4.2. And then you can see your mean values printed out below, and again, SAS uses the same format to convey information about pairwise comparisons and the respective statistical significance. So we see that even with Bonferroni adjustment, the never smokers are different than both the former and the current smokers, but the current and former, of course, do not become significant when we add these a more rigorous and conservative statistical hypothesis test. And then finally, I wanted to show a proc box plot. Box plots are often very helpful just to give a quick visualization of the data. And the basic form of a box plot in SAS is to use the box plot procedure. So you specify proc box plot, name your data set, and then you need to use a plot statement. Within the plot statement, you simply cross-tabulate the dependent variable with the explanatory variable. So the dependent variable should come first, followed by an asterisk, followed by the explanatory variable, and a semicolon, and that's all you would need to run a basic box plot. One important note about box plot is that the data needs to be sorted in ascending order of the grouping variable, or in other words, the explanatory variable, which is smoke in this example. So prior to running this box plot, you need to make sure that the data set is sorted by smoking status. In most cases, it's unlikely that it would be, so you would simply use a proc sort to get the data set sorted, and then run your box plot. We can go over to SAS and take a look at that. So rather than running a proc contents and checking to see whether or not my data set is sorted by smoking, because I doubt it is, I'm just going to quickly run the proc sort because it does not take much time. So my data set smoke2 is now sorted by the smoke variable, and then I'll run the box plot, and here are the results. So we see the distribution for systolic blood pressure according to smoke level 1, smoke level 2, and smoke level 3. Now, I've provided some supplemental code below so that you could go into the N. Haynes example and think more about sort of a real-life data set and determine how systolic blood pressure varies according to levels of obesity or gender or age, various frameworks or hypotheses that you may want to test, and I'll leave that to you. This is simply explaining to you how the box plots are formatted and a reminder of how to interpret them. So in summary, we went over some basic concepts of ANOVA. We talked about how to use proc ANOVA in SAS. We went over some techniques for getting quick and useful multiple comparisons results. We talked about proc box plot. And one final thing I wanted to note is that generally speaking, if linear regression is used and set up appropriately, for example using proc GLM and proc reg, which is discussed in the linear regression lesson of this course, you can usually forgo running actual proc ANOVAs because those regressions also include ANOVA analyses and they provide the results by default. However, some people really prefer to just stick to an ANOVA setting and have data structures that only require ANOVA, one or two categorical variables predicting some continuous outcome variable. But if you get into situations where you're interested in smoking, but you also want to adjust for a number of other variables, several of which are maybe continuous in nature and aren't as well suited to the ANOVAs we've been talking about so far, then linear regression is a nice option. And I recommend that you check out the lesson on linear regression to get more information about how to set up various categorical variables within the context of a linear regression.